And 5, 4, 3, 2, 1. Not yet, because I'm going to test this and make sure it's still working. Okay. Alright, hi, I am Kyle Tucker, and this is my overview of the family of error detecting algorithms called cyclic redundancy checks, or CRCs. Now, the reason we need error detecting processes like this is because hardware is noisy. And I don't mean noisy in that it makes a lot of noise. I'm talking about channel noise. And that is any random variation in signal through a channel. And when I say channel, it means any way that information gets from point A to point B. It could be the circuit and cables inside your computer, or it could be the network in your home. It could be the networks between you and another computer on the internet. Any way for data to get from one place to another. That's what is called a channel here. Noise occurs in any electronic hardware. It's just a natural occurrence, and it can be caused by anything from thermal conditions, thermal changes, to material defects, radio interference, you name it. And anyway, every now and then, information traveling through a channel runs into that noise and gets corrupted. So the data that the sender sent is not the data that the receiver receives. And obviously that's not good. So, if it's a text file, you could correct a few characters in it easy enough. But if it's a program that's being transmitted, then you probably have a broken program. So that's where error detection comes in. Error detecting algorithms, they are ways to look for corruption to data that is caused by noise or anomalies in a communication channel, so that a receiver can request that a message be resent if errors are detected. And one such method, of course, is the cyclic redundancy check. The idea was introduced in 1961 by UF professor William Wesley Peterson. And they're based on the idea of polynomials, which we'll get to in a minute, and appending a check value to the message that's being sent. A check value is just basically a function of the content of the message, where a certain function is performed on the message and the value is appended to the message before it's sent. The receiver can verify the check value using the same function once it receives the message. And of course, if the data doesn't match, then the data is no good. It's more than just a fancy checksum, but if you look at it in terms of what it's doing to the message, it performs the same general function as a checksum. And an actual checksum is, like it says, it's a sum. It's just a sum of the bytes of a message, modulo 256. So the remainder of the sum of the bytes divided by 256. That's your checksum, and that's what gets appended to the message. So here's an example, and you can see between the original and received the difference in that highest byte. And so what will happen is when the receiver gets that message and sums the bytes, the check value will be different than the check value that was sent. So it's clear that something didn't quite match up. Now, let's look at polynomials. The idea of polynomials might sound a bit intense just by the name, but it's not. It's really just a different way of writing a bit string. And what you do is basically consider each bit to be a coefficient of an x term of some degree, and that degree is the position of the bit in the bit string. So here's an example where you can see how that is converted. And another notion that's a little different than what you might expect is arithmetic when it comes to polynomials. It's really just binary arithmetic with no carries, which in terms of addition and subtraction does something really interesting. It turns them into the exclusive OR operation, and they're both equivalent. Addition and subtraction do exactly the same thing in this math called polynomial arithmetic. And because of that, it really kind of destroys the notion of order, or the magnitude of a term. Magnitude in polynomial arithmetic only depends on the position of the highest bit of the term, the highest one in the term. So 1, 0, 0, 0 would obviously be greater than 1, 0, but 1, 1, 0, 0 isn't greater than 1, 0, 0, 0 because their most significant one bit is in the same position. So the basic idea behind the process of the CRC is to define a generator polynomial of a certain width, and I see that's a typo there, and you add that many bits to the end of the message, and that's just empty bits, zeros. So if you have a polynomial of width 4, then you would append 4 bits. And when I say of width 4, that there's actually 5 terms in a 4-bit polynomial, because you've got the 0th term that you have to consider, the 1 at the very beginning. So you would actually have, the 0th term, the 1st, 2nd, 3rd, and 4th. So 5 terms in a 4-bit polynomial. So once you've augmented the message with that number of bits, then you divide that augmented message by the generator polynomial. And what will happen is at the end of the operation, the remainder will be in the extra bits that you added. And that remainder is your check value. And the factors that make up a good polynomial depend on us thinking of corruptions as error vectors. So basically, the exclusive OR of the transmitted message and some sequence of bad bits. So a single bit error looks like this, with just a single bad bit. And a burst error would be like this, an unbroken sequence of bad bits. And the idea is to design your polynomials so their multiples resemble those error vectors as little as possible. And just as a couple of examples to expand on those, to detect single bit errors, just choosing a polynomial with at least 2 bits set to 1 will guarantee that. And when it comes to burst errors, any polynomial of a width n, call it what you will, can detect any burst errors of that length or smaller. And though it's not included on the slides, polynomial of width n has I want to say about a 99.8% probability of detecting a burst error larger than that width as well. There's a lot of applications to CRCs because they're easy to implement in both software and hardware. They're a common choice for detection in storage and networking applications. Those are kind of the two main domains. Protocols like serial ATA and that of the SD card, they use CRCs when reading or writing persistent storage. And a little more interestingly, at least to me, is individual packets sent over Ethernet. They each include their own CRC, and a packet is limited to 1,500 bytes by Ethernet standards. And a lot of Ethernet transmissions are a lot bigger than 1,500 bytes, so they're made up of many, many, many packets, and each packet has its own CRC. So you can detect errors on a very granular level with the way Ethernet packets are designed. And the beauty of it is if If an error is detected in a single packet, then just that single packet can be resent as opposed to having to resend the entire message, which obviously has a lot of benefits in terms of network traffic and load, and obviously frustration on the user too. But as good as CRCs are for detecting errors from channel noise, they're bad for detecting intentional or malicious corruption, or for cryptography, because they're, for one, reversible. They're not authenticated, so a message and its CRC could be altered in transit in the middle, between sender and receiver without detection. A receiver doesn't know what it's supposed to have. It doesn't know what the sender had when it let go. It only knows what it received and what polynomial it's supposed to examine it with. So if data is altered in a certain way, then the polynomial could still calculate the desired result and not detect an error. And that concludes my presentation. Thank you.